Hello everybody! In this video, we're going to learn about tangent lines for multivariable functions. But before we talk about multivariable functions, let's quickly review this topic from Calculus 1. Let's assume that we're given a curve, y equals a function of x. Now it's pretty easy to calculate a secant line. A secant line is defined as a line that passes through 2 points on the curve. So you can pick your 2 points, maybe call them x1, y1 and x2, y2. You can calculate the slope between them, and then you can use one of those points to calculate the intercept. Now, in this case, the 2 points we would calculate for a secant line, we'll call one of them x, so the corresponding y-coordinate will be f of x. And then the next point, x2, we'll just add some small number h to x. The corresponding y value will then be f of x plus h. So the slope between these 2 points, y2 minus y1 over x2 minus x1, we could rewrite that as f of x plus h minus f of x all over x plus h minus x. And there's a little bit of simplification you can do on the bottom as well. You have an x and negative x, those cancel out, leaving you with h on the bottom. So that would be the slope of a secant line. Now, one of the key ideas in calculus is the idea of a limit. As this value h approaches 0, and as that gets smaller and smaller, these 2 points move closer together, and that's indicated with the notation limit as h approaches 0. The secant line becomes a tangent line. A tangent line only intersects a curve in a single point. And so as h gets smaller, this point moves closer and closer to that point. And the slope of this line will approach the derivative of the function at that point. So then we'll be left with a tangent line. It's a line which intersects a curve at this one point, and the slope of that line is equal to the slope of the curve at that point. Now, in multivariable mathematics, there's actually lots of tangent lines to a surface at any given point. Right? If you choose, say, a point right here, there might be a tangent line going along the x direction or going along the y direction, or all sorts of directions in between. Let's focus on one of these possible tangent lines, the tangent line in the x direction. In other words, we want the x-coordinate to vary and the y-coordinate to stay constant. Now, as the x-coordinate varies, as we move along this direction, right, in the xy plane, the height on the surface will vary as well. Right, so the slope will be the change in the height as x is changing. Right, we could write that expression like so. Right, the change, the displacement h, is being applied to only x. So we have this particular limit, which leaves us with the partial derivative of z with respect to x. So that'll be the slope of the tangent line in the z direction. And so our ultimate goal is going to be to use partial derivatives to calculate the parametric equation of a tangent line. We know parametric equations of lines have this form: L of t equals slope vector m times t plus p. We'd like to calculate this equation of this tangent line to a given surface along the x direction. And that's actually a very complicated sounding goal, but as I hope you'll see, it's rather straightforward using the partial derivatives that we previously learned. In order to write the equation of a tangent line, we need 2 pieces of information. We need a point on that line and the slope of that line. Now, if we're given the values x equals a and y equals b, then the coordinates of that point, p, x, y, z, well, x is equal to a and y is equal to b, we can substitute a and b into the function f to give us the value of z. So that's how you'd calculate this point. In order to calculate the slope, well, the slope is the change in the x direction the change in the y direction, and the change in the z direction. And we want to know how much is each one of these coordinates changing as the variable x is changing. Sometimes the change in x is called the run and the change in y is called the rise. I'd like to propose that we call the change in z the raise. And so the run, rise, and raise. But really the important thing is to calculate each one of these changes as x is changing, we're calculating partial derivatives. Dx by dx, dy by dx, and dz by dx. Now, how quickly is x changing with respect to x? Well, this ratio is going to be 1. The second fraction, dy dx, well, if x is the variable, x is changing, and y is being held constant, that means there is no change in y. There is 0 change in y as x changes. So the second derivative, or this second component, this partial derivative, is equal to 0. And then this third component, dz dx, these are the partial derivatives that we learned how to calculate in a previous lesson. Right, so this is the partial derivative calculated and evaluated at that point. So the slope of the tangent line, vector m, is equal to the vector 1, 0, and the partial derivative dz dx. And similarly, if we want to calculate the slope of a tangent line in the y direction, we need to calculate the change in x, change in y, and change in z, each one of these as y is changing. And if the tangent line is moving in the y direction, that means y is variable and x is being held constant. Therefore, dx dy is equal to 0, dy dy, that ratio is 1, and dz dy are the partial derivative that we learned how to calculate, again, in a previous lesson. And so this is how we would calculate the slope of this tangent line. Let's do an example to make these abstract concepts more concrete. Let's say we'd like to calculate the tangent lines for this function z equals x squared times y cubed at the point x comma y equals 1 comma 2. Right? To calculate the equation of a tangent line, we need the point on the line. And so we'll take the given x and y values and also substitute them to get the value of z. And we have the point 1, 2, 8. And that will be on both of the tangent lines. Right? When we say tangent lines plural, that means we're going to look for both the tangent line in the x direction and also the tangent line in the y direction. So we need both the partial derivatives of this function as well. To calculate the partial derivative of z with respect to x, we treat x as the variable and y as a constant, so we need to find the derivative of x squared times a constant. That derivative is 2x times the constant. So we have 2xy cubed, and we like to evaluate it at 1, 2. So we plug in 1 for x, 2 for y, and we arrive at the value of 16 for this partial derivative. Similarly, we need to calculate the partial derivative dz dy for this function. When calculating dz dy, y is the variable, and we treat x like a constant. So this function, in this case, you can think of as a constant times y cubed. The derivative of a constant times y cubed is that constant times 3y squared. So this partial derivative is that constant, x squared, times 3y squared. Now we have this function. We'd like to evaluate it at the point 1, 2. So let's substitute 1 for x and 2 for y. And then when we multiply that out, we'll get 12. So the partial derivative with respect to y is equal to 12. And this is the information that we need to calculate our slope vectors for these two tangent lines. The tangent line in the x direction is L of t equals the vector 1, 0, 16 times t plus plus the point 1, 2, 8. The tangent line in the y direction is L of t equals 0, 1, 12 times t plus the point 1, 2, 8. And that's how you calculate the tangent line to a surface in these two directions. Let's do another example. Let's say we want to calculate these two tangent lines to this function. The function z equals 3x plus the square root of x times y plus y squared. And let's assume we'd like to calculate that at the point xy equals 4, 3. First, let's figure out the point which will lie on both of these lines. The point P, which is equal to x, y, z, we need the value of x, we need the value of y, and then the value of z. We'll substitute these values 4 and 3 in for x and y. When we calculate that, we're going to get 12 plus 6 plus 9, and so that should give us 27. Then we need partial derivatives. Let's see, the partial derivative of this function with respect to x, we'll treat x like a variable. The derivative of 3x is 3. The derivative of the square root of x times a constant is equal to, well, we can think of the square root of x as x to the 1/2 power and then apply the power rule. So this derivative is 1/2 x to the negative 1/2 times the constant, y. Remember, the derivative with respect to x means we treat y as a constant, so the derivative of y squared, which is a constant, is 0. Rewriting this expression, we can think of it as 3 plus 1 over 2 square root of x times y. Evaluating that at the point 4, 3, we have the answer 3 plus 3/4, which is also the fraction 15/4. So that's the partial derivative with respect to x, and we'll need that value when calculating the slope of the tangent line in the x direction. Next, to calculate the partial derivative dz dy, in this case, y is our variable, and we think of x as a constant. The derivative of 3x, that's the derivative of a constant, that's 0. That doesn't even appear here. The derivative of a constant times y is just the constant. And the derivative of y squared with respect to y is 2y. So here's our expression. We'd like to evaluate it at 4/3. That turns into the square root of 4 plus 6. That's 2 plus 6, which is 8. And that's our partial derivative with respect to y. We need that for the slope of the tangent line in the y direction. With all this information calculated, now we just need to write down the equations of the lines. The tangent line in the x direction is L of t equals 1, 0, 15 over 4 times t, plus the point 4, 3, 27. The tangent line in the y direction is L of t equals the vector 0, 1, 8 times t, plus the point 4, 3, 27. And there's another example of how you calculate tangent lines. Let's do one more. Let's calculate the tangent lines to a plane, just in general. Right? A plane is a flat surface, so some of the calculations are a little bit easier. And here, let's assume we have the general equation of a plane to start. So that's ax plus by plus cz equals d, where a, b, c, and d are constants. Now the first step is to rewrite this expression so it looks like a function, z as a function of x and y. So we need to move the ax and the by terms from the left to the right-hand side. They become negative. And then we divide everything on both sides of the equation by c. And we're left with this function. And let's assume we'd like to calculate the equation of the tangent lines at the origin. So at the point xy equals 0, 0. First, we need a point on this tangent line. And so that point is x equals 0, y equals 0, and then plug 0, 0 into this equation. Right? As we plug 0 in for x and 0 in for y, that cancels out a lot of this equation. Now, this plane does not pass through the origin. When x is equal to 0 and y is equal to 0, z is equal to d over c. Right? So the plane passes through this point. Next, let's calculate the slopes. To get the slopes, we need the partial derivatives of this function with respect to x and with respect to y. The partial derivative of z with respect to x, we treat x as a variable and y as a constant, and so that partial derivative is actually just negative a over c. The partial derivative of z with respect to y, treat y as a variable and x as a constant, and so here's our variable, and everything else is a constant. The derivative is just the coefficient of y, in this case negative b over c. Right? So in this problem, we're working with a plane. It's important to remember that the slope of a plane in 3 dimensions is a constant, kind of like the slope of a line in 2 dimensions. Right? So unlike our previous problems, we haven't needed to plug in the values of x or y into these partial derivatives. So at this point, we're just ready to write down the equations of the tangent lines. The tangent line in the x direction is L of t equals the slope vector 1, 0, negative a over c times t plus the point 0, 0, d over c. The tangent line in the y direction is L of t is equal to the slope vector 0, 1, negative b over c times t plus the point 0, 0, d over c. And so these are the tangent lines to the plane. Now, you might remember, I'm a big fan of the philosophy, you learn math by doing math, so here's an exercise for you to try. It gives you good practice with calculating partial derivatives, and also writing down slope vectors and finding equations of tangent lines. So I'd like you to find the equation of the tangent lines to this function, z equals x squared times y plus y squared plus x. I'd like you to find both tangent lines, both in the x direction and the y direction. So you'll need to calculate the partial derivatives dz dx and dz dy. You'll need to evaluate them at this point. That'll help you find your slope vectors. You'll also need to evaluate this original function at the point xy. That helps you find a point on the tangent lines. And then you should be able to write down the equations of the tangent lines, following the same pattern as the earlier examples in this lesson. And that is how you write down the equation of a tangent line for a multivariable function. Thanks for watching.